All right. Now, we've learned about normal distribution. So what we're going to do is look at a set of data and see whether we could model it using the normal distribution model. How appropriate it is. So by the end of the lesson, you should understand the suitability of the normal distribution in a variety of contexts and solve some problems involving discrete normal variables that require a continuity correction, adjustment, especially binomially distributed random variables. All right, let's talk about modeling data. Normal distribution are a really useful tool for modeling data from many natural occurring random variables. Now, if we have a set of data, how do we actually decide whether it is normally distributed or not? Again, think about what we need to do. Two things. Two main things we got to think about when we're deciding whether or not your data is actually normally distributed. Number one, let's look at the symmetry, whether the data is symmetrical. If the data is fairly symmetrical about the mean, it should be alright to use normal distribution to model it. However, you also need to think about the proportionality of the data. Even if the data is actually symmetrical about the mean, you need to think about the proportionality, for example, the 68%, 95%, and the 99.7% rule. Alright? Something like you should think about looking at the standard deviation. The standard deviation from the mean, the data which is occupying standard deviation, one standard deviation from the mean on both sides should be about 68% of the data. Alright? So those are quite important. The 68%, 95%, and 99.7% rule should be used as a test. So both of them together, you can see if the set of data is actually suitable to model as normal distribution. Now, let's have a look at example 1. Decide with reasons whether or not it would be reasonable to model each of the following data set describing using the normal distribution. A data set is negatively distributed. So, if the data set is negatively distributed, it will look something like this. Right? Yeah. So it is actually not symmetrical, is it? No. So is it suitable?
No.
No. So you need to give the reason.
Within 3 standard deviations,
so you need
this
to
negative
explain
question
why.
is impossible.
So it is not suitable because it is not symmetrical. Now, the next one. A data set has 50% of its data point within 1 standard deviation of the mean. So we know that for normal distribution, within 1 standard deviation of the mean, that should be 68%. Correct? And 50% is just way too small. If it is something like 67%, yeah, of course, that's fine. Or 69%, that's all right. So something like 50%, I would say that it's not suitable because it's too small. The proportion is not right. All right? Now, the next thing, the concentration of cholesterol in the rodent species was found to have a mean of 142 units with the standard deviation 86 units. How are you going to think about how could you work out whether it is suitable?
3 deviations.
All right. Now, if you look at 1 standard deviation is 86, what happens if it is 2 standard deviation?
Negative, not possible.
You get negative the other side, the other way. Correct? So if it is mu take away 2 sigma, it will be a negative number, which is, I think it's negative 30. Yeah? So think about whether it could go into negative.
Nope.
So this is another test. So if it is in negative, you can't have a negative cholesterol level, concentration of cholesterol. So it is not suitable. So all 3 are not suitable. Do you agree with me? You don't have to write down exactly what I've written down. That's just a sample answer. It may not write the way that you want to write when you explain. You don't have to follow me word by word. All right, what about 1D? The mean and standard deviation of 1697 measurements were calculated to be 67.4 and 15.6 respectively. It was found that 646 of the measurements were within one standard deviation of the mean. All right. Now, think about the proportion. 646 over 1697. How many percent are there? 38.07%.
Not enough.
So is it going to be all right?
No.
No. So you need to be able to justify it. All right, the next one is an interesting one. 2595 freshwater fish of a particular species had their lengths measured. The mean and standard deviation was found to be 1.1 meter and 0.5 meters, respectively. 650 of the fish were longer than 1.49 meters. So, do you think it is possible to use normal distribution?
Wait.
I'm going to wait. I'll let you think about it first. Right. So if you draw it,
1.9 is a weird
so
number.
this is
So it's like 1.68.
1.1 meter. That's a mean. All right. And then somewhere here, 1.49 meters. That's the proportion that's over 1.49 meters. How are you going to work this out? So I've sketched the standard deviation,
Oh, norm
the
CDF.
normal distribution graph for you.
Norm CDF.
Can you?
Sure, and if they're not equal, then you say no, right?
All right.
Yeah.
Do you think it is possible?
Right.
Okay, I'm going to wait.
Our deviation is 0.58.
Oh, it's turned up now.
Oh yeah, it's possible.
Is it?
I think,
Alright.
yeah.
Okay. So, now, I've written down the normal distribution. If x is normally distributed 1.1 and 0.58 square. So, the probability of x greater than 1.49 should be 0.2507. 4 decimal places. Remember, 4 decimal places. And the proportion is 0.2505. Yep, it looks right. Alright? Now, what about if you look at
Yeah, it's close enough.
mu take away
Oh, so you still got to
2
check
sigma.
the other
You get minus 0.16.
one.
So therefore,
It's not
it is
possible.
not right. So you could use one way of checking, the proportion is correct. But if you look at the other
What if the,
side of the
the
mean,
fish was facing this way?
you
right?
get a negative.
So that's positive measurement.
So, a
The
negative
fish
value-
is facing this way,
Oh yeah.
and then you get a negative
You
measurement
can't
facing the other way.
actually, therefore cannot actually use standard deviation. These are the questions that you need to do a couple of checks.
Yeah, yeah, yeah.
Oh,
It will trick you. Alright? So do both checks. One check, yes, the proportion is alright, but looking at the other side, that's no. You can't do that. Alright, now, use your class pad. If you use your class pad to generate a list of 200 observations from a binomial distribution, we've got success of 0.5. Alright. What I really want you to think about now, if I ask you to generate success rate of 0.2 and success rate of 0.8 or 0.1 and 0.9 and have two lists, and what is going to happen? So this one looks pretty much like a uniformly distributed data, correct? It's quite symmetrical. Now the thing is, whatever you generated, because it's random number, it may not be the same as what I've generated. Alright? So let's try generating with a probability of 0.2 and 0.8 as well. So you've got three lists. 0.2, 0.5 and 0.8. I want to show you
I
something.
don't think it's possible.
So it
Alright, I want to show you something.
doesn't seem to really load. So can we do 100 observations? 200
You
doesn't
can do
really
100,
work.
you can do 200. I did 200 because I want it to be a little bit more obvious.
But how do I
This is what I've generated.
break?
Alright? So you can see that this bit here,
Doesn't work. Does yours work? Yeah.
Yeah, it's working out.
is probability of 0.5. I think this is probability of 0.2. I think. I cannot remember what I did. And probability of 0.8. Now, what we can do, can you all focus on here for a minute, please? If you look at the data set we have got from 0 to 100. We are looking at the whole range from 0 to 100. So here, the red bit, you can see that it's sort of fairly symmetrical, and you can draw a
What do you make it?
normal distribution, right? Yeah? Now, what about the blue? Is it skewed?
Shit.
Yeah? It is skewed to the right. You can't see the data, it's small. If you generate more, there will be some data. It's skewed to the right. Whereas the green is actually negatively
Sick
skewed or
mind.
skewed to the left.
Doesn't even
Yeah?
look good.
So, now, if you look at it, think about it. Can you model the data?
Red one.
The red one.
With the red one, you can.
Yeah.
Yeah.
Yeah, because it's pretty obvious. Now, the next bit we're going to look at is when we think about something like this, it is fairly symmetrical as well, can we? Isn't that right? So the next bit we're looking at is, can we restrict it within that part
Yes.
and we model it? So that is what we're going to look at on Thursday, the sample proportion from there onwards. How could we use the sample proportion to model? Alright, so that's, yes, with this, plotting all three, you can see that
I
this
didn't even
is
know you could do this. Like,
definitely, you can model it because it's symmetrical.
Yeah.
This one, positively skewed. And this is negatively skewed. Yeah? So you can see why. One is pretty straightforward, you can do that, but by the time you do this, you've got a few checks that you need to do. Alright, I will show you when we come to that bit.
Put in some
Alright,
fresh
next bit.
batteries this morning.
I got 2 bars still. I'm fine. What?
Alright? Now,
But it's not that hard.
what we need to do,
One question.
the normal approximation to the binomial. Despite the fact that the normal distribution is defined for continuous random variable,
Middle.
it can sometimes be used to approximate probabilities from a binomial distribution, such as if your binomial distribution, number of trials and number of successes,
It's a
is
DRV,
NP.
so it's only discrete
then
values.
if you want to
Kind of
model
like-
it,
Yeah.
we need to model it as a normal
Yeah,
distribution
it's just
of
like if you put
NP
red, blue.
and
Yeah.
NP times 1 minus
Zero.
P, where P is approximately 0.5. Can you please write that down, please?
Yes.
So, this is actually binomial, number of trials and the probability of success. This is normally distributed, the mean and the variance. The mean and the variance, yep.
How close to 0.5 does it have to be?
0.5, 0.6 approximately.
Okay.
Yeah, points, yeah. 0.6.
Zero doesn't have to be right.
Plus or minus 0.1, I would say.
Alright.
It could be
Yeah, I
red,
would
black,
say.
green, and blue.
Okay.
Like it's
We
not.
say what?
But I will confirm that with
Some
you.
actual value.
Yeah, I think plus or minus
It's just like a
0.1.
net. It's you just,
So-
0 is here.
0.4 and 0.6, I think. 0.7 will be too far away.
Yeah, yeah.
Oh, okay.
Yeah, sure. How close does it have to be?
Plus one.
All right.
0.1.
Now,
0.1.
so let's have a look at example 3. We now have a random variable x, which is binomially distributed. We've got a number of trial of 60 and success rate of 0.5. So that's n and p. Can we therefore write the whatever you call it, the distribution for normal distribution? Can you do that, please? Based on the formula that I've given you. All right.
30.
You all right, Button? Button, you okay?
15.
Oh,
Yeah. Compare the probabilities. Oh yeah, true.
all right. Now, you've got that, and you can work out. The mean for the normal distribution is 30, and it is sigma square, all right? So when I was solving this problem, I've forgotten to do a square root of 15. Just remember, xn is the mean, and this is sigma square, all right? So you need to work out the standard deviation, which is therefore square root of 15 square, okay? So explain why it may be suitable to approximate the distribution of x using approximate normal distribution. Defining the distribution as xn. What happened is, you know that the probability of this happening is you can see that this is symmetrical. The probability is 0.5. So 50% of the time things will happen under 60, and 50% of the time things will happen the other way. So the data would most likely be symmetrical. The probability of success is 0.5. Therefore, it could be an approximate normal distribution. Now, can you compare the following probability, please? Use your calculator. You need to use your calculator. Use your one is binomial, which is x equals to 31, and the other one is normal distribution. Now, with normal distribution, can we have xn equals to 31? Probability of that, what would that be?
Equals 31. X equals 31, 0.0993.
That is x equals to 31 divided by xn if it is normally distributed.
0.
0. Yeah.
Alright? So think about it. Now, we said that we can model it, but the difference is 0.09. What about the next one? We'll go through and explain a few other things in a few minutes. So if it is less than for binomial, if it is less than 31. So it has to be less than or equals to 30, correct? And 0.2918, that's what I get.
Yep.
Whereas for normal distribution, you don't have to worry too much. You can just put it as 31, 0.2991. Now, why? We said that we can actually model the binomial because it is symmetrical using normal. But look at the probability. It's a big difference. What you need to do is do adjustment to the normal distribution. You need to do some adjustment so that it can mimic the probability. So this is called the continuity adjustment. Because the binomial distribution is a discrete distribution, and the normal distribution is a continuous distribution. So we talk about a continuity adjustment, where we use the normal distribution to approximate probability from a binomial distribution. So it's technically outside the cost, but you need to know that, alright? So you need to understand that. So one way of performing adjustment for continuity are to use an adjustment factor of 0.5, plus or minus 0.5. So you've got the table there. If it is x equals to k, you know that probability of x equals to k equals 0. But then, if you do a continuous, you think about k take away minus 0.5, k take away 5. Alright? So you've got that range to look at. And whatever is discrete is right in the middle of those two. Yeah?
Do you have to memorize that whole table?
Sorry?
Do you have to memorize that whole table?
No, you don't have to. You don't have to.
Then how?
That's slightly outside the course, but I just want all of you to be aware of it, that's all.
Oh,
I think if a question like this come up, you will be told how to adjust.
Oh, okay.
Alright? You'll be told how to adjust. So you need to think about, for example, how you could adjust this. And this is just a table. You don't have to memorize this. Plus or minus k. Plus or minus 0.5. So if this case, can we do the continuity adjustment of plus or minus 0.5 for normal distribution of 31? So you need to think about 31 take away 0.5, which is 30.5, and 31 plus 5 is 31.5. So if you compare that, you've got 0.0994, which is pretty much the same. 4 decimal places, that is close enough. So the adjustment is 0.5. Now what about going back to the second adjustment? Again, if I do that adjustment, 28, I reduce it continuous for the normal distribution, I reduce it to 27.5, and then because it's less than 31, so I use 30.5, and you can see that the result is close enough.
Yeah.
Alright, I'm going to stop here now. That's an exercise in Sadler for you to do.
Yeah, direct. Sir, could I go get a drink?
Yep.
I'm done.